Yeah, so in the last class we have discussed the different kind of OS structures that are available, like layered. Yeah, yeah. So we were discussing about the different kind of OS structures that are available. One is layered approach, wherein you can find the layer zero is the hardware, above which you have the different kind of layers, such as kernel, APIs, libraries, middleware, and then at the end probably you may find the user applications, okay, or user tasks. So a typical operating system layer, say layer M, consists of data structures and a set of routines that can be invoked by higher layer. Layer M in turn can invoke the operation in lower level layers. Similarly, each layer is implemented only with the operation provided by lower level layers. A layer does not need to know how these operations are going to be implemented, but rather what operations it does. The main advantage of layered approach is simplicity of construction and debugging. The layers are selected so that each user's functions are operation and services of only lower level layers. The approach simplifies debugging and system verification. The first layer can be debugged without any concern for the rest of the system. Once the first layer is debugged, its correct functioning can be assumed while the second layer is debugged, and so on. If an error is found during the debugging of a particular layer, the error must be on that layer. Coming to the next kind of structure is a microkernel system structure. It moves as much from the kernel into the user space. Mac is an example of a microkernel architecture where you can see Darwin, based on this Mac. Communication takes place between the user modules using the message passing mechanism here. The benefits that we get out of it is easier to extend to microkernel. It is easier for us to extend into a microkernel. It is easier to port the operating system into new architectures. It's more reliable, more secure. Detriments performance overhead of user space to kernel spaces by the message passing. So we look at the microkernel system structure here. The application program, file systems, device drivers, and all on one layer, below which you probably find all the kernel modules, right? So in kernel modules, all such user services that it requires from the kernel, right, or OS, such as inter-process communication and memory management, CPU scheduling, all that. And below which, of course, you have the hardware. I mean, you don't have much layers here. You have the user module, or user mode. In user mode, you have the user modules, and then you have in kernel mode. The next to user mode is the kernel mode, in which you have the kernel modules, below which you have the hardware. So many modern operating systems implement this loadable kernel modules, uses object-oriented approach. Each core component is separate, each talks to the other over known interfaces. Each is loadable as needed within the kernel. So as and when it is required, you can probably load such kind of modules. Means you not to load the modules all at once. Rather, depending on the requirement, you can do this. Overall, similar to layers, but more flexible. Like for example, Linux, Solaris, etc. Hybrid systems. In practice, very few operating systems adopt a single strictly defined structure. Instead, they combine different structures, resulting in hybrid system that addresses performance, security, and usability issues. For example, Linux is monolithic because having the operating system in a single address space provides very efficient performance. However, Linux are also modular so that new functionality can be dynamically added to the kernel. We cover the structure of three hybrid systems here: Apple, Mac OS, iOS, and Android. So the mobile OSs or laptop OSs generally you find they are the hybrid kind. Okay. Architecture of Mac OS, iOS, where you can find kernel environment, Darwin at the bottom, over which you have code framework over which you probably find the application framework and over which you find user experiences or APIs, and then you have the applications. Darwin uses a hybrid structure and is shown here in the below diagram. Darwin is a layered system which consists primarily of the match microkernel and the BSD Berkeley system socket, Unix kernel. So here the bottom you can see match kernel, the memory management modules, IPC, scheduling, IO kit and XTS all part of the match kernel, over which you find the match traps. With the help of the traps, you enter into the kernel, right, from the user rather, right. And then parallel to which you have the BSD POSIX threads, our system calls here going to be implemented with the help of this POSIX, right. Android. Coming to Android, it's developed by Open Handset Alliance, mostly Google now. It is completely owned by Google now. It's an open source, similar stack to OS we find in this architecture. It's based on Linux kernel, but modified. It provided processes, memory, device development, driver management, and it adds the power management as well, because power is also one kind of issue that you probably see with mobiles, rather, right? So it's all even power management is being taken care here by switching off such applications which are not in use, by making use of the hybrid kind, where we have in microkernel we have seen only the required modules are going to be loaded and the others are not. So in similar fashion, rather, you can find there in Android as well. The apps are developed in Java. You have a Dalvik machine, Java Dalvik virtual machine as part of the Android architecture. You find right, all the system calls are going to run in that particular Dalvik virtual machine. It's very similar to that of your JRE kind, right? Java runtime environment. Java class files compiled to Java bytecodes, then translated to executable, then run in Dalvik virtual machine. Libraries include frameworks for web browsers, database like SQLite and multimedia small libs, etc. Power is gone. Android architecture. Fine. For Android architecture, I have one video separately recorded on my YouTube channel. You can listen that, right? For mobile OS as well. Anyway, so I would like to continue this with OS generations. Coming to OS generations, operating systems are designed to run on any of a class of machines. The system must be configured for each specific computer site. Sysgen program obtains the information concerning the specific configuration of the hardware systems used to build system-specific compiled kernel or system tune. Can have general, a more efficient code than one general kernel. System boot. When power is initialized, what happens? The system gets booted, right? You have a firmware called ROM, yes, which holds the boot code. The operating system has been made available to hardware so that the hardware can start. Small piece of code, which you call it as bootstrap loader, which is stored in ROM or EPROM, locates the kernel, leads into the memory, and then starts the operating system and in your system, right? Sometimes two-step process where boot block at fixed location loaded by ROM code, which loads bootstrap loader from this sometimes, right? But bootstrap loader is not going to be part of your system ROM, but rather it will be loaded from hardware. Otherwise, it is going to be a part of firmware like ROM or EPROM, from where immediately once you switch on the system, it gets start executing, so that the OS programs are going to be loaded from hardware too. Common bootstrap loader you find is the grub, right? Allows selection of kernel from multiple disk versions, kernel options, kernel loads, and the system is then running.